Welcome back. In this video, we'll explore the relation between electric fields and electric potential. This is a key concept in understanding how charges interact with each other in an electric field. Then later on, we'll learn in depth about the behavior of conductors in electric field. Let's begin. Consider 2 points A and B in an uniform electric field E. They are separated by a small distance del r. We know that potential difference del V between A and B is equal to work done in moving a unit test charge, positive test charge, from point A to B. So, del V is equal to force on unit test charge into the distance AB, which can be written as E dot del R. Since the angle between the electric field and del R is opposite in direction, that is 180 degree, del V is equal to minus E del R. We can also write it as E is equal to minus del V by del R. Here del V is a potential difference, E is the electric field strength, and the work is done against the electric field, which is why we add a negative sign. This relation tells us that the electric field E is equal to the negative rate of change of potential with respect to distance at that point in the direction of electric field. It is also called as potential gradient. Remember, electric potential is a scalar quantity, but potential gradient is a vector, as it is numerically equal to electric field. Now, from the above relation for a uniform electric field, we can write E is equal to VA minus VB by D, where VA and VB are the potential at points A and B respectively, separated by distance D. Let's go over an example. A point charge Q is at the origin of a Cartesian coordinate system. The electric potential is 400 volt and the magnitude of electric field is 150 Newton Coulomb inverse. At a point X, calculate X and Q. So this is the Cartesian coordinate system. We are said that the charge Q is at origin. The electric potential V is 400 volt and the electric field is 150 Newton Coulomb inverse at a point X. We need to find X, right? Here. First, recall the relationship between electric field and potential. E is equal to V by X. Since this is origin, this distance is also X. So, we find X to be V by E, which is 400 by 150, which is 2.67 meter. Next, we have to calculate the charge Q. We know that E is equal to 1.45 epsilon naught Q by R square. Substituting 1 by 4 pi epsilon naught is 9 into 10 to the power 9 into Q by 2.67 square. This is 150. If you solve for this, you get Q is equal to 11.9 into 10 to the power minus 8 Coulomb. Now let's move on to the behavior of substances in an electric field. Based on charge conduction, substances are broadly classified as conductors and insulators. In solids, conduction of electricity usually takes place due to free electrons, while in fluids it's typically due to ions. Conductors, like metals, have free charge carriers which allow electric currents to flow when an electric field is applied. On the other hand, insulators are substances that have no free charge carriers, meaning they do not conduct electricity. Common examples of insulators include wood, ebonite, glass, quartz, and mica. Substances that have electrical conductivity somewhere between that of conductors and insulators are known as semiconductor. The ratio of electrical conductivity between good conductors and good insulators is typically of the order 10 to the power 20. Now let's focus on how conductors behave when placed in an electric field. Conductors have free electrons that are not tightly bound to their atoms, allowing them to move freely within the conductor. However, there is no net transfer of electrons from one part of the conductor to the other in the absence of any applied electric field. The conductor is then said to be electrostatic equilibrium. Consider a conductor placed in an external electric field. The free electrons inside the conductor accelerates in a direction opposite to that of the electric field. This results in buildup of electrons on the surface ABCD of the conductor. The surface FGHK in the figure becomes positively charged because of removal of electrons. These charges create their own field which are in a direction opposite to E. The transfer of electrons from the surface FGHK to ABCD continues till E becomes equal to the newer electric field E1. Such a state of electrostatic equilibrium is reached usually in 10 to the power minus 16 seconds. We can say that equilibrium is reached almost instantaneously. If there is a cavity inside the conductor, the electric field inside the cavity is zero. These results are true for a charged conductor or when charges are induced on a neutral conductor by an external electric field. This property of conductors is called electrostatic shielding, a phenomena of protecting a certain region of space from external electric fields to protect delicate instruments from external electric fields. They are enclosed in a hollow conductors. For example, when you are inside a car during a thunderstorm, the metal body of the car provides shielding from lightning because the electric field inside the car is zero. Conductors in electrostatic equilibrium exhibit a few important properties. There is no electric field inside a conductor. The electric field outside a charged conductor is perpendicular to the surface of the conductor irrespective of the shape of the conductor. Any charge on the conductor resides on the surface of the conductor. To summarize, the relation between electric field and potential is fundamental in understanding how charges interact in an electric field. Electric field is the negative gradient of electric potential, and this concept helps us to explain how conductors behave in such fields. If you found this video helpful, don't forget to like, share and subscribe. See you in the next video where we will explore more exciting concepts in electricity and magnetism.